We just had an excellent colloquium, the ITC, by Anne-Marie Madigan, who will speak in a few minutes about dinosaurs in the solar system. She gave an excellent talk about the other textbook phenomena that she discovered over the past few years that were very enlightening. And then we'll hear from Catherine Espaillat, that is visiting us from BU, not very far, just across the river. And she's giving something that we arranged once per month or so to talk about equity and inclusion. And the title would be on mentoring models, a multi-method approach. And after that, we'll hear from Shany Danieli, who is graduating at Yale. Is Shany here? Yeah. Oh, great. And she will talk about the galaxies with no dark matter. Is that possible? And finally, we'll hear from Shmuel Bialy. We do allow some men to speak every now and then. And he will talk about the thermal phases of H1 gas from solar to primordial metallicities. So Anne-Marie, please.
Okay, so I'll get right to it. I'm going to start with dinosaurs. So dinosaurs first appeared about 240 million years ago, and they became the dominant terrestrial vertebrate until about 66 million years ago. And we're all quite familiar that there was an asteroid or a comet impact, and it killed off about 75% of species, including all non-avian dinosaurs. We think the dino impactor was about 10 kilometers in diameter, or about 2 to 3 times the size of Comet 67P, that we know of quite well. It's plotted here suggestively with downtown LA, so about 2 to 3 times the size of this comet, which isn't that big, right? But the problem was it was traveling at about 40 times the speed of sound when it impacted the Earth. So it hit in the Yucatan Peninsula, in a town, modern-day Mexico, called Chicxulub, near a modern-day town. And the impact depressed the crust of the Earth by several kilometers, and it gouged out a crater that's about 200 kilometers in width. So if you were a dinosaur in the general vicinity, you were vaporized. But not just dinosaurs, a lot of the Earth's crust in that region was vaporized and got sent or thrown up into the atmosphere. It then spread until it enveloped the entire globe. So it wasn't just dinosaurs in the general vicinity or hemisphere of the Earth that were affected. Everybody had a bad day. And so this is roughly the timeline of what happened. So we had superheated liquid rock thrown up into the atmosphere.
The mic does not seem to be on.
Oh, I'm not wearing a mic.
Oh, you're not wearing
That would be it. Hello. I'm just going to hold it.
Okay. So we had liquid rock thrown up into the atmosphere, and when it hit the cold of space, it re-solidified into glass droplets and started to rain back down all over the globe. And so it was raining glass, which isn't brilliant. But what was worse is the friction of those glass droplets with the atmosphere created a huge blast of heat that hit everything on the surface of the planet. And so that was particularly bad if you weren't able to burrow under soil or under rock or in water. So we think nothing larger than a raccoon survived this initial blast of heat. So we're talking about hours after impact. In addition, this blast of heat ignited worldwide forest fires, and we know that because of the layer of rock that was laid down at the time has a huge amount of soot from all these forest fires. So it's raining glass, everything's on fire, including the sky. Not brilliant for a T-Rex. The next stage is that all that soot and the dust from the impact remained in the atmosphere for months. And so that blocked out sunlight and photosynthesis collapsed. And so that's really what started the true mass extinction event. Finally, when those particles drifted back down, what was still in the atmosphere was all the CO2 and the other greenhouse gases that primarily came from the forest fires, but also from that vaporized carbonate rock that was thrown up into the atmosphere. So we think after the nuclear winter, we very quickly went into a global warming phase. So this event was uniquely bad for the dinosaurs, but it doesn't stand alone. So there's a quite uncontroversial correlation between impacts from space and mass extinction events. So I'm just going to show one of these plots. So this is crater formation rate on the y-axis versus millions of years going back in time here. And the stars point out the largest impact craters that we've been able to identify on Earth, whereas the extinction events are denoted with these arrows. So this is the Chicxulub event at 66 million years. Okay, so that's quite uncontroversial. What is more controversial, and I think this is like the Planet 9 of geological sciences, half believe it, half don't, is that there appears to be a periodicity to these cratering events. So if we just start here at 36 million years, 66, 94, 113, you might come to the conclusion that there's some type of periodicity on the order of 30 million years. So very controversial, and obviously there's a lot of observational biases, particularly as you go back in time. It gets harder and harder to identify these craters. But for the purposes of this talk, the rest of the 5 minutes, let's just assume this is true. So what are the explanations that we have for the periodicity in the cratering record? So far there are three, I would say, top theories. The first is Planet X. So there's a massive outer solar system planet that keeps perturbing comets in the outer solar system. A stellar companion to the sun. This is sometimes called Nemesis. This would be a brown dwarf, something very dim that we haven't identified yet. Or the third is a disk of dark matter. It would need to be a special form of dark matter that we don't currently know about, but is not currently ruled out. I think Gaia is going to tell us more about this. And this is actually a theory written up into a fantastic book by Lisa Randall, who's in the physics department here. What they all have in common, however, is that they all propose some new astronomical object to explain this periodicity, something outside what we already know. So what I'm proposing, with a smile on my face because the data may just be nonsense and there's no periodicity whatsoever, is that comets periodically throw each other onto radial orbits via their own mutual gravity. You don't need anything new. Okay, how would this work? This is a lunch talk. I don't want to pummel you with equations and stuff. So I'm going to draw something extremely simple, just a schematic, and hopefully get across the message. So in the outer solar system, let's think of hundreds of AU. There are, I think, lots of bodies out there on very eccentric orbits. And they're not all going to have equal masses. So what I'm drawing schematically here is the red orbit is a more massive cometary body, whereas the blue ones are less massive. Let's say the mass difference is about 100. Doesn't matter too much. They're going to gravitationally interact with each other. Now, people who are at my colloquium just half an hour ago are going to be at an advantage because they know exactly what this is. This is the angular momentum of an orbit given by r cross v. This is a torque, or a rate of change of angular momentum, induced on an orbit due to gravitational forces given by a radius times the gravitational force vector f. Okay, but in this configuration that I've set up, everything should be in balance. We're going to look at what happens this massive comet. Everything's in balance. There's an orbit here that matches an orbit here, so nothing's going to change with angular momentum. But these orbits are going to precess. That means the orbits are going to open out because they feel the influence of each other. And the more massive orbit feels less mass than the less massive orbits, because there's a difference in the masses. Okay, so if we stay in the frame co-precessing with the more massive comet's orbit, you see a shift like this. Oh, sorry, that wasn't a shift. This is the velocity vector. Everything precesses in the opposite direction. Like this. Okay, so in the frame co-precessing with this massive comet's orbit, everything kind of seems to move faster than it does. So now you're lopsided, remember that velocity vector, the force is going to be stronger on this side. And so the torque this orbit experiences is going to increase its angular momentum. If you increase the angular momentum of an orbit, you make it more circular, has more angular momentum. So I had lots of fun with Keynote preparing for this talk. This orbit's going to get more circular. Again, if you were in my colloquium earlier, I just show you a boat and you're like, oh my gosh, I absolutely understand what you mean now. If you have a small eccentricity vector, or like you're in a kayak and it's short, it's easier for you to process. That's maybe a bit too much of a jump right now. But once you get more circular, you process faster, essentially, than what you were doing when you were in more eccentric orbit. And so what happens is that you process faster than the less massive comets, and now the imbalance goes the other way. And you feel a torque that makes you more eccentric again. And so this is just a toy diagram of what should happen to a massive comet in a sea of smaller mass comets when they're on eccentric orbits. I blacked off part of this diagram to just show you this is the eccentricity. Now this is from actual simulations, not just a schematic. With same color coding, so this is the massive body's eccentricity. Please ignore the downward trend for now. That's to do with mass segregation that's too high in the simulations. But as you can see, it undergoes eccentricity oscillations back and forth just because of that differential precession rates, and it's interacting with different orbits in the sea of smaller mass comets. Is that me? Am I done? Okay. Yeah. What I want to point out is this is the mean eccentricity evolution for the surrounding sea of comets. And obviously it has to oscillate with the same oscillation period, but going in the opposite direction to conserve angular momentum. But what this misses is that most of the sea of smaller mass comets are doing nothing. And this change, this increase here in eccentricity is actually driven by a few that feel really, really strong torques from the more massive comet. This is my second last slide. It's a bit of a busy plot, but what I've done here is reverse the eccentricity evolution. Did somebody shout with me? No. So this is 1 minus eccentricity. So all the eccentricities of these small comets start off at the same value. And there are these times where they're more likely to jump to higher eccentricity orbits. And these correspond to the times when the more massive comet is at a lower eccentricity phase of its oscillation. I've run out of time. The time scale for this oscillation, where you get like these dangerous, like danger zone parts of your solar system where comets can actually impact the inner solar system planets, that relates to the mass ratio of the central object times the sea of smaller comets. If you put in 10 Earth masses, so this is a huge if, we do not see 10 Earth masses out there, but for other reasons, this is what comes out of a different project, that there could be 10 Earth masses in this region. The oscillation period you get is 30 million years. It just kind of falls out. So that's nice. I've run out of time. I will just leave this up, and if anybody wants to ask me about this later, please do. Thank you.
Very interesting questions. Go ahead.
So is it, if I understood correctly, the largest change right now is eccentricities for the most massive objects?
The opposite. So the least massive objects, because they're interacting with a comet that's more massive than them, their eccentricity oscillations are much more extreme.
So I guess my general question was then, would then be possible to like make predictions on what like the eccentricity distribution should be in the hyperbole or in the Oort cloud in this model, and if we can test it with current or like near future distributions?
Yeah. So to get that time scale, I'm assuming all the mass is distributed at like hundreds of AU, and so there's a lot of ways you can do this, like with different mass bodies out there. You can have one that's like Sedna or something that's more like Planet 9 or something like that. So there's different ways we can do this, but all of them should lead to a prediction that we should be able to detect this thing at some point, depending on what its magnitude is now. So it depends where you put it, and there are various ways to actually get this time scale. Or the time scale is wrong. that there is no periodicity, but there should be predictions that we can test with this.
There was a Nature paper just a week ago talking about an increase by a factor of a few in the impact rate based on craters in the moon versus the Earth that people analyzed. Have you looked at that? Because that can be another constraint on the model, the change in the impact rate as a function of time, going back hundreds of years.
Yeah. I looked at it briefly, and then...
Other questions? Aaron?
With each passing period, does the maximum eccentricity decrease? And how many periods would this self-consistently continue before it's...
Yeah, if you want like the same period for like the entire age of the solar system, there are a few things that need to happen that may not be realistic. Like you cannot be changing your semi-major axis rapidly. So in our simulations, the massive body actually interacts with small mass bodies and just like decides to go inwards. So that's something that you couldn't have enough kind of two-body relaxation that you're actually mass segregating out your system. But otherwise, as long as you have the same semi-major axis, and the amount of mass you're interacting with is roughly the same. I mean, the amount of comets you lose when flying into the solar system is really low mass. The periodicity should stay the same.
Last question, Erwin.
About the first part of your talk. You didn't mention anything about the Deccan traps.
It's true, yes.
Which I think is still somewhat controversial as to the relative importance in the extinction of organisms between the Deccan traps and the impact.
Yes. So I didn't want to go into other theories for mass extinctions. So that's why I keep saying controversial and tentative and may not be real. But it's not just mass extinctions, or it's not just impacts that are invoked for mass extinctions. It is a release of a lot of greenhouse gases from the Deccan traps and things like that that could be causing them. Very true. And that could have a periodicity too.
Yes.
Yeah.
We need to move on. Let's thank Anne again.
Because I mean, the creators, okay, you somehow collect the rocks and no one likes that. Maybe something fossils or like copper and things. We don't really know. We probably never will.
All right, so we'll go ahead and get started. I'll be talking about mentoring. Mentoring is important for equity and inclusion because it helps grant access. It helps people gain knowledge that they can use to navigate through the system. So this is a shorter version of a talk that I gave this past summer here as part of the Latino Summer Initiative. So this is a shorter version of that. So if you were at that talk, I hope hearing about this again gives you a new, interesting perspective that maybe you didn't think about the first time around. And if you weren't at that talk, someone invited me to give this, so it's not that bad. So it's not the worst way to spend the next 10 minutes. All right, so at least one person thought it was useful. All right, so if you Google pictures of mentoring, this is what you get. And this is the image that a lot of people have of mentoring. You're lifting multiple people up. There's a lot of ravines. There's a lot of pulling up. Here, like, I will help you not just be better, but the best, like me. And I'm here to disabuse you of this idea of mentoring, of being a mentor and of being a mentee. First, I think it's a big disservice to mentees that one person is going to save you, and if they don't save you, it's their fault. So a lot of what I'm going to be talking about is putting some of the burden on the mentee to learn and reach out. And also, I think a big barrier for mentors is that, I don't know about you, but I don't think I know everything. And when someone, says, oh, you're going to help me save my life, I'm like, I don't know what I'm doing with my own life. So I think it sets a big burden for people, and people opt out of mentoring because they don't think they have enough knowledge to share. So you all have some knowledge to share. You all have lived experiences in your life, so you all have something that you can share. So you're all qualified to be a mentor. So you don't have to adhere to this vision of mentoring. All right, so why am I here giving this talk? Why am I asked often to give talks about mentoring? I'm an astrophysicist. I study planet formation. I'm not a sociologist. This is not a science database talk. This is a talk to encourage discussion, and I'm sharing my learned experiences with you, and we can always follow up afterwards. I'm at Boston University, not that far away. So I do have some specific area of expertise in mentoring. I coordinate, and I've been coordinating and running mentoring programs with different styles of mentoring, like I'll be talking about in the next few slides, for about the past decade. And one of these was actually here when I did my postdoc at Harvard, running the Women in Science, Technology, Engineering, and Math Wisdom mentoring program. All right, so 3 quick questions for the next few minutes. What is mentoring? What is the role of the mentee? What is the role of the mentor? So very basically, mentoring is a partnership between 1 or 2 or more people, and we'll get to the more than 2 people in a couple of slides. And it's meant to share knowledge, to support, encourage people to reach their maximum potential. And there are different types of mentoring, so different types of mentoring models. So a lot of people are most familiar with one-on-one mentoring, where a senior person mentors a junior person. There's this little peer mentoring, where members of similar rank get together and share what they've learned and help each other out. And then there's also group mentoring, where you have 1 or more senior members who are mentoring at the same time multiple junior mentees. So a more efficient way of mentoring. Okay, and before I get into the mentoring models, I did want to give a nod to unconscious bias. So unconscious bias is important when it comes to mentoring because unconscious bias is a natural phenomenon that we all are susceptible to, and mentoring is about relationships between people. So it's difficult to disentangle unconscious bias from mentoring, and it's natural, it's not to be ashamed of. All of us go through this, and if you want to learn more about it, there's actually been a lot of research here at Harvard. There's this website, the Implicit Association Test, where you can teach yourself about implicit bias. And I mention this because it affects both mentors and mentees. A lot of the informal one-on-one mentoring, it's a mentor that sees some potential, something in someone reminds them of themselves, and so they choose to mentor that person. So you can see how unconscious bias can factor in there if you're just seeking out people that look like you. And it's the same thing the other way around. A lot of mentees fall into the trap that if someone looks very different than me, didn't have the same life experiences as me, they don't have a lot to offer me because they don't know my experience. And it's been my experience it's actually the people that have the most different backgrounds, the most different paths in their careers that I learned the most from because they figured out how to do things in a different way. So implicit bias, unconscious bias affects both mentors and mentees. All right, one-on-one mentoring. So I'll go through the advantages and disadvantages of each model. So the advantages, it facilitates networking. It's a great way to be connected with someone that's senior in the field, specific to astronomy, someone that's probably on panels that can give you advice. They probably referee papers. They can give you advice on how to write good papers. And also they can give very useful discipline-specific advice. So if you're choosing a senior person in your field. The disadvantages, the one that's most common is that it may not be a good fit. This is especially the case if it's through a formal mentoring program where it's just one-on-one matching up. Some people just don't gel, they just don't get along. A mentee may feel less comfortable truly being honest and sharing difficult experiences with the senior person because, for example, I can't share all of my negative experiences in planet formation with someone who's senior in the field of planet formation. What if they come away with this negative impression of me, that I can't handle things, right? That's things that some mentees think about. So that can make things difficult. And also, there are a lot fewer senior people than junior people. So it's not possible to match up every single junior person with a senior person. It's a big disadvantage of the one-on-one mentoring. Peer mentoring. So this is where you have people in the same kind of stage in their careers. The advantage is that you are exposed to more experiences, different experiences that people are going through at your same level. And you're also more likely to get more recent experience from someone that's gone through something much more recently. So I do not remember what it's like to apply to grad school. I sit on grad admissions committees, but I don't remember that feeling. So I wouldn't be a good mentor for someone who's trying to navigate those feelings, because I just don't remember it. And also, this increases access for underrepresented groups, because you don't have to be selected. You get to opt in to these kinds of programs. Disadvantages is that you have a limited range of experience with seniority. So there are people who, the people who are at the similar rank as you, they're not going to know what's down the pipeline 5 to 10 years in someone's career. What's going on now that can have ripple effects to the future. So you have a limited range of experience. And also, some people just don't think that they can learn that much from their peers. So sometimes it's hard to recruit junior members into these peer mentoring networks. And then group mentoring. So this is where you have one or more senior people mentoring a group of junior people. So advantages, you can have more than one experienced opinion. So hopefully you get exposed to more experiences. You can serve many more mentees, so many more junior people. And the mentees there can also share their experience. So a lot more discussions there. Disadvantages, confidentiality becomes more of an issue. You have to state clearly at the beginning and check in throughout that everything that is said in a mentoring, a group mentoring, a mentoring circle stays confidential. And scheduling becomes very difficult when you're trying to manage more people. All right, so in my experience with running those different mentoring programs, I've done all different kinds of flavors of those models in the programs that I've run. And like I said, they all have advantages or disadvantages. If you're interested, if you're interested in mentoring or setting up a program, let's talk afterwards. I'm happy to share my experiences. So now, some role of the mentee. So some things, some best practices that I've learned for both mentees and mentors that I share with you to perhaps help you get more out of your mentor-mentee relationships. So the number one question a mentee should be asking all the time is, what do I need and where can I get it? So you want something, so you have to go get it. Most people, not because they don't care, but it's just because they don't have time, are not constantly checking in with you and seeing how things are going. So you need to decide for yourself, what do you need, where can you get it? And here's some examples of things that you need. Professional development, how do I write fellowship proposals, emotional support, how do I go dealing with a paper rejection, role models, who can you seek out that you kind of want to follow the same career path that they did, access to opportunities, who has experience sitting on panel reviews, admissions committees that can share some knowledge with you to improve your chances moving forward, and feedback. How can you get, who can give you the best feedback? And if you can imagine, this is a very wide range of needs. It's very unlikely you're going to find it from one person, and it's also very unhealthy to find it from one person. You should be reaching out to many people many times in order to get different kinds of experiences, different kinds of information with these different areas that you need help with. And also some other things to keep in mind when you're a mentee. You also want to continue maintaining the relationship with the mentor over time. So you want to be respectful of the mentor's time. Usually if you're interacting with someone that's more senior than you, they have a lot more commitments that are time sensitive than you do. So it's not that they don't care or don't have time. Actually, it might literally be that they don't have time. They just are overcommitted. So just be respectful of the time. Show up on time. If you have to cancel with enough notice. Be sure you follow through. If you say, I need you to read a fellowship proposal for me, send them the fellowship proposal. Show appreciation, stay professional, so set boundaries. Don't let the personal overlap with the professional. And then the number one question for the mentor is to ask, how can I be of help? So very similar areas that I outlined for the mentee. And because I'm out of time, I just want to highlight something that we find difficult, I find difficult, is to share failures as well as successes. Successes tend to be more visible. The failures, we kind of have to volunteer that. And I think it's important for junior people to see that there are many failures along the way that we just don't talk about often. All right, and then that's it. So I'll end here. Thank you very much.
Obviously, another important rule that mentee follow, and that's don't always follow the advice that you're
Yes.
given.
Yes. That's why it's important to get many different kinds of advice and pick the one that's best for you.
Mesh.
So this group mentoring model, so Is it just a round table and you've got the senior and junior people all sitting and talking at the same time? Is that the idea?
That would be the ideal, or a square table like this. You
Oh,
can do this over here.
round table would be better.
Round table would be better. We go to do it like here. So yeah, that's basically the idea. And if you're running a formal mentoring program, it's more convenient to for scheduling. Like usually you have institutional support for that. But if you're running something that's informal, I participate in a few informal things. It's just meeting up at a coffee shop that has a big enough table. Panera, they usually have big enough tables. So there's different ways.
But with an agenda and like a meeting.
Yeah. It depends on the style of the mentors and mentees. I didn't get into it, but I advocate for having some kind of agreement at your first meeting for what do you want to cover. Do you want to keep it very formal about we're going to go through these 5 things and when we're done with 5 things our relationship is over, or do you want to just you meet up once a month and whatever is on your mind you can talk about. So you can decide that at the very first meeting.
We have exactly those forums among the faculty as well. We have an
great.
informal lunch meeting and we have faculty meetings where we have items.
That's great.
I have a question. For a department, would you think it's important for them to set up some kind of formal mentoring structure with grad students and things like that and just assign mentors and mentees? Or do you think it should happen more naturally? And maybe we can say quickly the reason I'm asking this is at Boulder we do have this kind of formal structure, and you can just end up paired, both as a mentor and a mentee, paired with somebody, and it just doesn't click, and you never want to do it.
Yeah, it's tough. I mean, I'm an advocate of having any kind of formal mentoring program because that's how a lot of people, that's what they think of mentoring. So I think anything is better than nothing. And then that's why I also strongly advocate going after these informal relationships on your own. And those kind of formal programs could be revised a bit with constant check-ins, how are things going. But I advocate for any kind of mentoring program being in place. And maybe we can touch base a little bit more afterwards to dig deeper.
Try to do your best.
Yeah.
So Catherine will be giving the CFA colloquium later today. We all look forward to hearing about the planets.
Yeah, I do have data there. So.
It's not Catherine.
Oh yeah.
Okay. Hi everyone. I'm excited to be here and share with you what I think is a very exciting discovery about galaxies missing or lacking their dark matter. And this is a joint work with the people listed here that we recently published in a series of papers. So I'm going to start by giving you the punchline and say why is it even interesting, and then I'll take you through the details. So we think that every galaxy forms and lives within a dark matter halo. However, last year, we discovered 2 galaxies that seems to be consistent with having no dark matter at all. This is really interesting because it raises a lot of questions about how can we even form these galaxies. So let's go into the details. So as I said, galaxies form and live within dark matter halos, and dark matter really determines the way the galaxy will evolve. In particular, we think that the amount of luminous matter that you can see here is really determined by the amount of dark matter in the halo, and we expect to have a lot of dark matter in all galaxies. But especially in dwarf galaxy systems, we expect this galaxy to be really dark matter dominated, and to have sometimes about 1,000 times more mass in dark matter than in luminous matter. So these dwarf galaxies are really excellent laboratories for testing dark matter theories. The problem is that it's often really difficult to find these dwarf galaxies, especially outside our local group, so further away than 3 or 5 megaparsec from us, because dwarf galaxies are really low surface brightness. So even with the best telescopes that we have, they usually look like these really fuzzy blobs, and this is kind of a typical surface brightness for dwarf galaxies. They look like these really low surface brightness blobs, and they're just really challenging to discover. In the last 4 years or so, we've been going after these galaxies with the Dragonfly telescope that was designed specially to detect low surface brightness phenomena. So what's really cool is that basically what happens is that every field that we point Dragonfly at, we find a lot of new discoveries and a lot of new galaxies. One of these fields that wasn't special when we observed it is the field around this elliptical galaxy here, NGC 1052. That's a galaxy group at 20 megaparsec. And we immediately detected these 6 blobs. But one of them, NGC 1052, or DF2 in short, was especially intriguing. So let's take a closer look on DF2. So this is how it looks in the Dragonfly image. It looks like this very smooth galaxy with maybe a little bit of clumping. But when we pulled the Sloan images, this is what we see. This is what we saw. So the diffuse light almost is basically barely detectable or just detectable in the Sloan images, but we saw all of this clustering of point sources that are kind of not even resolved really. So this really intrigued us to go and look after these point sources and check whether, first of all, what are they? And then whether they're actually related to this diffuse light that we detect in the Dragonfly images. So we got HST images, and in the HST images, we just resolved these point sources. We then got Keck spectra of more than 50 compact objects in the field. And most of the objects in the field turned out to be background galaxies or Milky Way stars. But 10 of them, the ones that you can see here, were extremely similar in size and magnitude, color, and velocity. So combining the Keck spectra with the information that we had from the HST images, we concluded that these galaxies, these compact objects are globular clusters that are bounded to this galaxy, that are bounded to the system. So we use these velocities and these globular clusters to trace the gravitational well of the system. So here, what you can see on the left, the yellow points, are the individual velocities of each one of these globular clusters. And even without quantifying anything here, you can see that all of them lie comfortably within this red curve, which is how we would expect the velocity to distribute if the galaxy was composed only out of stars, so no dark matter. The black curve here is how we would expect the velocity, the radial velocity, to distribute of tracers if the dark matter had a normal dark matter halo. So we infer the intrinsic dispersion of the galaxy, of the system, using these 10 velocities, and we calculate the velocity dispersion, which you can see here on the right, and we infer a velocity dispersion of 7.8 kilometers per second, where only from the stars we expect a contribution of 7 kilometers per second. So we concluded this galaxy has basically very little to no dark matter at all. So this is really interesting, and it drew a lot of attention from the galaxy community. And in the last 8 months or so, there were about 40 papers written only this galaxy alone. And we ourselves wanted to actually have a confirmation that this galaxy lacks dark matter, because there's still quite a lot of tail here that leaves room for higher dispersions. So the more precise way really to measure the dispersion of the galaxy is to measure the stellar velocity dispersion of the stars in the stellar body of the galaxy. So not only the globular clusters, that way you get way more tracers. But this is difficult, again, because the galaxy is low surface brightness, and if you want to be able to measure dispersion that is lower than 10 kilometers per second or so, we need really high spectral resolution. But just in time, fortunately, there was a new instrument commissioned on Keck just last year, just about a year ago, the Keck Cosmic Web Imager, or KCWI, and we were awarded 2 nights in October, 3 months ago, and we got our spectrum that we really waited for. And I'm going to show it in just a second. I just want to say that if the velocity dispersion is indeed really low, we expect the absorption lines in the spectrum to be very narrow. So here's the spectrum after some data reduction. And you can see that we observe a lot of pretty strong absorption lines, H-beta, iron, and magnesium. So we can fit the spectrum with templates and measure the velocity dispersion. This is the quantity that we're going after. And here is the result. So from the KCWI measurement of the stellar velocity dispersion, we measure a dispersion of 8.4. And not only that it's consistent with the measurement from the 10 globular clusters, as expected, the constraints are better, okay? And then it's still consistent with what we would expect from the stars alone. And then, as of 3 weeks ago, DF2 is not alone. We now have another galaxy, DF4. We're not great with naming galaxies. This is what it is. And DF4 is basically an identical galaxy to DF2, also in the same group. It has the same physical size, it has the same stellar mass, and it also has this really spectacular population of really bright and really unusual globular clusters. So we repeated this exercise. We got, again, Keck spectra for the 7 globular clusters. You can see here. So again, here are the velocities of the individual globular clusters. You can obviously see that we had better conditions because we have smaller error bars. And again, without even measuring anything, you can see that the velocity distribution is pretty narrow. And here is the velocity dispersion that we inferred. We get a dispersion of 4 kilometers per second, where the expected dispersion from the stars alone is 7. So this is another galaxy consistent with no dark matter. So I just want to summarize and say that last year we've discovered 2 galaxies that seem to have very little to no dark matter. Each one of them has this very unusual population of globular clusters, which I can give another talk on because they are really interesting. And they may or may not be related to this dark matter deficiency that we see in the galaxy. This is really just the beginning, and maybe it's worth highlighting that these galaxies weren't really predicted before, so this is a sort of a pure discovery. And there are still, of course, many open questions. The first one, and maybe the most interesting one, is how can we even form these galaxies in the known lambda CDM and galaxy formation framework? Some suggestions include that maybe the dark matter was stripped from the galaxy when it interacted with the host galaxy here, the elliptical galaxy NGC 1052. But this doesn't quite work with the fact that the morphology of the galaxy looks very, very regular. With very deep imaging, we don't see any tidal features, any stripping. And then it doesn't quite work also with the properties of the globular clusters. Another suggestion is that maybe this is a tidal dwarf, so gas was ejected for formation of a more massive galaxy at high redshift, and then this galaxy will form. But then if you look at some tidal dwarfs, they really look different. They look like they have a lot of tidal features, and again, it doesn't quite work with the globular clusters population. Observationally, looking into the future, we just completed a very wide field survey with Dragonfly, 400 square degrees. We should be able to detect these kind of galaxies. We're going even deeper, actually. And we're also going through an ultra-wide field survey of thousands of square degrees to try and find more of these galaxies, understand how common they are, and whether we see them in other environments, maybe in the field or in clusters. And I'll take questions now. Thank you.
As a graduate student, you went through a very interesting experience because you found something completely unexpected, right? And obviously, the scientific community will not be quiet about it, so you got some papers that were criticizing the results. And
yeah.
Can you just summarize very briefly what the arguments were, why people claim that the results are not valid, and what's your response to that?
Yeah, so there were 2 points that were debated. The first one is the statistical methods that were used to infer the velocity dispersion from distant tracers. I have to say that even, so we adopted one statistical method, and then adopting a different one raised the velocity dispersion by a little bit. But in order to address it, we got this KCWI time. So, we actually get the velocity dispersion of the stars. Some people, of course, said that maybe the globular clusters don't follow the gravitational well, really. They follow some substructure in the galaxy, in the halo. So again, this KCWI data also solve this problem. And some said that maybe the globular clusters are not really part of the system, and maybe they lie in a thin disk, which is now ruled out because we have this second galaxy. And then the second debate was about the distance of the galaxy. So some people measured the tip of the red giant branch of the galaxy and said that the galaxy is actually closer, and then most of the unusual properties kind of disappear. So we published another paper, several papers, addressing this point. And of course that we're trying to get more HC data, but we solved the problem with more data. And so we are convinced that the galaxy is actually part of the LGC 1052 group.
So did this data that you collected convince those other people that you're right?
Well, I think so. We actually presented this work in Princeton about a month ago, and it was much better than my presentation in Leiden this summer. So I think people are getting convinced slowly, and I hope we will get our HST time to actually measure the distance more accurately.
Okay, lots of questions. Let's start from here.
Yeah, so Andy Buchert was here about a week ago, and he was telling about the correlation between the number of globular clusters and the halo mass. So here you have at least 10 globular clusters, which would correspond to a halo mass of like 5 times 10 to the 10.
Right. Yeah.
And then you were comparing the Earth dispersion of globular clusters with a model with 6 times 10 to 10. So how do you match these two together?
So, as Andy showed, actually, that for low mass galaxies there is a lot of scatter, right? So their relation really works for many orders of magnitude, but for much higher galaxy mass. So yeah, I mean this is an outlier, yeah, I mean it's not clear, but this is an observation, and I think basically the relation between global clusters and halo mass is very tight for high masses, but not so much for low masses.
And it's also not a fundamental physics.
Right, no, yeah,
So
it's
you don't
a
have to
scaling
worry about
relation,
it.
of course.
It
Yeah.
just happens to be. Any other question?
Do you make any assumptions about the form of the dark matter of the low density profile? It could be that the dark matter is there, but in places that you would expect.
Yeah, so I didn't even show you any I didn't even show any dynamical mass calculation here. I only show the velocity dispersion. So we don't do any further steps to get. But of course, you can use the Wolf estimator. You can assume different core cuts. You can assume whatever you want, and you can do genes modeling, which is probably the best thing to do. But here I'm only showing the velocity dispersion, so I'm not even doing this extra step. And even just the velocity dispersion is consistent with the one that we expect from the stars.
Any last question over there? Yes.
Have you investigated whether it could be formed by something like gas ejected by aging winds?
I didn't personally, but it might be really, it might be worth. There was another idea about quasar winds, for example, which I think is sort of similar. But again, it will need to explain both the dark matter deficiency and the globular clusters, which I didn't even say in the talk, but they have really weird properties. They're not quite similar to Milky Way globular clusters, for example, in the way they distribute in magnitude and color. So it will, I mean, we have a lot of work to do in terms of interpretation.
You have to keep in mind this rule that when you come up with a new result, at first people will attack you and say that it's wrong, but then eventually they will say it's obvious. I mean, there are papers coming in the future that will say it's very easy to understand. Shmuel.
Okay, so let me back up a little bit and talk actually not about the dark matter, but the normal matter, the usual matter we all like and know, and also going from observations more to the theory side. So let me start with a small overview of the ISM. The interstellar medium is the mean density of the interstellar medium is about 1 particle per cubic centimeter, but it's very highly inhomogeneous. Large volumes are occupied by the so-called hot ionized medium that is produced by supernova remnants that are expanding and heating the gas to millions of degrees. But most of the gas is actually not in this phase, but is actually neutral and is found in 2 phases, the so-called the CNM and WNM, the cold and warm neutral medium, which has a typical temperature of about 100 degrees and about 30 particles per cc or 50 particles per cc, and the warm neutral medium is about 10,000 degrees and has a density of 100 times smaller. You might notice that the pressure in each one of them is about the same, so they coexist at pressure equilibrium in the interstellar medium. If we dig deeper into the CNM, that's where we find these wonderful images of the HST and others of these magnificent molecular clouds that then gravitationally collapse and form new stars. Well, and all the other things that comes with the star formation, human formation, other animal formation, or whatever. Let me focus in this talk on the two phases, the cold and warm neutral medium, which are the bulk of the interstellar medium. Myself, I had quite a strong experience going through a big phase transition from the warm to cold neutral medium as I moved here to Boston this September. So most of the mass is found in these two phases. How do we observe these phases? Basically, 21 centimeter line, the spin flip transition of atomic hydrogen is the most direct way to observe H1, the atomic hydrogen. When the spectroscopy and absorption and emission is combined together, we can infer not only the column densities, but also the temperature of the gas. And the general picture that emerges is that in the galaxy, about half of the gas is in the warm neutral medium, 30% is cold, and the rest is in between. Very important is this, we find in the galaxy that the CNM and WNM can coexist. So we have a multi-phase where the cold and warm medium coexist at the same pressure. And this might play a very important role in star formation and regulation of star formation. The basic idea is that, for example, if you now suddenly increase the star formation rate by a lot, you get loose of this warm phase. You get loose of the cold phase. You hit the cold phase. You get loose of the cold phase. You have now just warm neutral medium. And warm neutral medium is less susceptible to gravitational collapse and star formation. And your star formation goes down back again to the normal rate. So this multi-phase structure of the interstellar medium might play a key role in regulating star formation in galaxies. Here in this talk I want to ask, what happens if you go away from the Milky Way towards other galaxies, perhaps even the first galaxies in the universe that had very much lower metallicity? Would you still have this multi-phase structure in the ISM? How different would be the CNM and WNM structures in these first galaxies? So to understand this, let's go back a little bit to the theory side and understand why do we get this multi-phase structure in galaxies. So the idea is very simple. We just assume thermal equilibrium and equate the heating rate here to the left and the cooling rate at the heating rate at the left and the cooling rate at the right in the interstellar medium. Heating in the interstellar medium of our galaxy is dominated by photoelectric heating. These are UV photons that comes from the stars, hit dust grains, eject very energetic electrons that then thermalize and heat the gas. This is photoelectric heating. Then we have also other heating mechanisms as cosmic ray heating, X-ray heatings, and other things. Cooling is dominated by Lyman alpha cooling at high temperature and fine structure cooling of carbon and oxygen at low temperature. But generally, it's Lyman emission cooling that goes as density square, where heating goes as density to the power of 1. So basically, what you get is as you increase the density here in the x-axis, the temperature at some point goes down because cooling becomes more efficient compared to heating. And these two temperatures that we get here, for 10 to the 4 for the WNM and about 50 to 100 Kelvin for the CNM, are not accidental. They have to do with the atomic physics of the energy separation of these two cooling mechanisms, the Lyman alpha cooling and C plus and O1 cooling, which gives you this flow of 50 Kelvin and 10 to the 4 Kelvin for the WNM and CNM phases. So this is the temperature as function of the density diagram. We can also multiply this by n and get the pressure in the y-axis, which is very useful. So this is just like rotating this by 45 degrees. And this is what we get. So the pressure is something that might be set from outside conditions in the galaxy. For example, from the weight of the disk, from turbulence, from the hot ionized medium. There can be different controlling mechanisms for that. But this is set by the galaxy. And then you can ask, okay, given some pressure, what are the phases of your interstellar medium. So what we get, if the phases is too high, if the pressure is too high, you just get a one-phase medium of cold neutral medium. If the pressure is too low, you just get the warm neutral medium at about 10 to the 4 Kelvin. But importantly, there's this strip, the multi-phase strip, where you can get two stable solutions for the temperature and pressure, the warm and cold neutral medium that coexist at the same pressure. And this is what we also see in observations of the 21 centimeter line. Quite remarkably, independent set of observations that trace the pressure through carbon show that indeed the pressure in the interstellar medium of our galaxy falls somewhere here in this multi-phase region, which is purely theoretical. But this seemed to coincide. So it's either a very nice coincidence, or maybe it has to do with the self-regulation idea that I discussed earlier. Now, what happened when we decreased the metallicity? This is the main thing that I wanted to talk about now. So when you decrease the metallicity, you have to take into account now also the chemistry and cooling and heating of H2, because once you come to low enough metallicities, you'd expect that at some point H2, which is independent of metallicity, will start to dominate over these C+ and O1 cooling, which fall with decreasing metallicity. So we modeled this chemistry and cooling and heating mechanism of H2, assumed thermal equilibrium and chemical equilibrium, and this is what we get. So this is the curve for solar metallicity, as we saw before. Now, at first, when you decrease the metallicity, actually, it becomes easier at first to get to the CNM phase. So the CNM phase happens at lower temperatures and lower densities. And this is because as you decrease the metallicity, you decrease the cooling rate, but you also decrease the heating rate, because heating is by photoelectric heating. And actually, you can decrease the heating rate even stronger than the cooling rate, because at lower metallicities, the dust falls faster than linearly with metallicity, some observations suggest. So at first, this curve goes down. If you continue to decrease the metallicity, however, and go to metallicities of about 1% solar, now at this point, heating is no longer dominated by photoelectric heating, but is now dominated by other mechanisms such as cosmic ray or X-ray heating, and become independent of metallicity. In this limit, as you decrease the metallicity, you just decrease the cooling rate, and therefore you must compensate by higher and higher densities to achieve thermal equilibrium. So these curves shift to the right. If you continue further to decrease the metallicity and now go to about 0.1% solar, thinking of this is like at the age of reionization or so, now H2 cooling kicks in. So if we didn't have the H2, the curve would go like this and this, exactly like the red one, just shifted by a factor of 10. But now here in this range, H2 cooling kicks in and cools the gas. But you can see that the H2, what it does, it shrinks the multi-phase region, and the multi-phase region now becomes smaller, and the curve is more smooth. Still, here in this region, C+ and O1 cooling dominate. Finally, at very low metallicities, or zero if you want, pristine gas, H2 cooling totally dominates over the entire range. You don't have C+ and O1 cooling, and what you get that you lose entirely the multi-phase feature. You get one phase ISM wherever you look at, whatever pressure you look at. So this is the result. Let me just summarize. We saw that at moderate metallicities, strong reduction in the photoelectric heating makes it easier to form the CNM, the cold phase. This is like the SMC or LMC metallicities. At very low metallicities, like the low metallicity dwarfs seen around, cosmic ray already start to dominate the heating. The multi-phase shrinks because of H2 cooling. And also you have to go to higher and higher densities and pressure to achieve CNM. Finally, at zero metallicity, you cannot have a multi-phase, you have a single phase medium, and the temperature decreases monotonically. This can have profound implications on galaxy formation and star formation regulation in the first galaxies. And the next steps are to look into simulations. And maybe, I'm not sure, we're looking into that, but maybe JWST will be able to detect this warm H2 phase in the first galaxies. Thank you.
Two quick questions. One is, as you go to these primordial phases, and this is something we discussed a couple of years ago, the CMB background is going to be 30, 50, 100 Kelvin. And since the H2 is formed on the dust,
no, this is gas phase already.
Just gas phase?
Yeah. So in this model, we assume that the dust goes superlinearly with metallicity below 0.2. So already below 0.1, you don't have any dust. It's all gas formation.
So then my second question is, have you considered the effect of HD? Even though deuterium is down by a factor of 10 to the fifth, HD does have a dipole moment.
Yeah.
And below 200 Kelvin is a more efficient coolant than H2.
Yeah, we thought, we include HD. At first, we thought that we might get this from the HD, the lower temperatures. But HD, the abundance is not high enough, and we still, at these temperatures and densities that we look at, so we're thinking about the bulk ISM that is still atomic. So the H2 here is a residual H2. It's not, so we're still modeling the predominantly atomic ISM. You still have a little bit H2, but it's mostly H1, and the HD is not, HD cooling is not efficient enough to cool below the H2 cooling.
The same is true about lithium hydride.
Yeah.
Because lithium
Yeah.
too rare.
Yeah.
Any other comments? Charles?
What assumptions, if any, are you making about cosmic ray heating? Because that's also believed to be tied to strong shocks associated with supernova events in the current Milky Way.
So our model of the cosmic radiating is actually very simple. We don't get into that too much. Basically, you have one parameter, which is what is the cosmic ray ionization rate, and given the cosmic ray ionization rate, you have a heating rate that is proportional to the cosmic ray ionization rate, and this is a parameter in our model. So indeed, if you go to first galaxies, this may change a lot. We don't know exactly how, and I'll be happy to hear if you have any ideas how this is connected to the metallicity, for example. But the main parameters is the cosmic ionization rate and the metallicity in this low metallicity regime. And also the UV, because the UV sets the H2 dissociation rate.
But of course, it's not just the production rate that may change, but also the confinement of the cosmic rays by magnetic fields, which makes it much more complicated.
So all this changes this parameter zeta, the cosmic ionization rate. So it comes back to the question, what should be the right value to take?
What are the error bars that you have on this ionization?
The error bars.
We just know what happens in our galaxy. In our galaxy, it's also very uncertain. We know that the cosmic ionization rate is about 10 to the minus 16 events per second, but there's like a factor of 10 differences between regions in the galaxy, between diffuse gas and dense gas, and also between historical epochs. So if you look back 5 years ago, 10 years ago, or 20 years ago, this value goes up and down. Not really, but just in the papers. Yeah. So we also, I didn't show, but we also investigate the dependence on this parameter. Basically, if you increase the cosmic ionization rate or decrease the UV intensity, this helps in some way to H2, because to H2 to form in gas phase, you need electrons, which are produced by these cosmic rays. So it helps produce H2, and H2 cooling becomes more efficient. This is generally the result, but this isn't,
We got to our time limit. Let's thank all our speakers.